Good morning, everybody. Answered lots of questions this weekend. Good morning, Michael. How is life? Getting there? Figuring things out? Almost done. Last week of material. Project's due tonight. Calc 2 So, what is going to be covered on your final exam if you have a Calc 2 test? Right now. Yeah, space engineering student. When you open up parameters.txt, it's going to be just, well, it's not one column. It should be 4 columns. It should have 8 rows, 4 columns. It's not a single column. It should be in scientific notation, though. You can't change that. But it's your table of values. Your frequencies are in the first row, or the first column. And your length, and masses, and then cost. So if it's a single column, that means you probably created your array wrong. The variable that you're saving, that array. Yep, you can still click the quiz. Michael Pa, if you open up your text file and it's got a bunch of weird symbols, that means you forgot the ASCII option. Space engineering student, if you use fprintf for the table, that's fine. You still need to save your code. You can use, so saving your code, or not code, saving your data. Saving your data and printing out your data are 2 separate things. You print things out with fprintf or disp, and then you save it with the save function. But either way, you need to put your data into an array. So yeah, Sophia, you can still take the quiz. It's fine. It's not a problem. Michael, use the ASCII option. Oh, sorry. Yeah. So get all that done tonight. Michael, you make a really good point. So I gave you guys the rubric for your project. If you want to kind of pick and choose what to focus on, look at the rubric. The rubric will tell you more or less what is more important. What are you going to be willing to lose points on? Are you pretty sure you did most of the rubric correctly? And maybe you didn't write your file out correctly, and you're like, okay, that's only 1 point on the rubric or 2 points on the rubric. I don't really care much about that. I'm done. My brain is shot. Moving forward. For your report, if you don't have much time to write your report, it's very important you do write your report. Communication is key and essential. But if you're running out of time, look at the rubric. Okay, where can I get some easy points? If I only have like a title page and some basic stuff, can I get a couple points? So you can use the rubric to kind of pick and choose as you move forward if you're running out of time. Also keep in mind that you can get points for something even if something else doesn't work. So you could, in theory, get all of the points for part E without finishing part B or part C. You could, in theory, get all the points for part D without finishing part C and your stuff being incorrect. So make sure you're not just stalling on something and you're spending forever when there's lots of points for you to still get. Also, as you're writing your report, it doesn't matter what your results look like. If you get results, that's fine. If you don't get results, if your results don't look like what they're supposed to look like, that's fine. Just write it in the report however it comes out. It's not that big of a deal. You're not going to get docked points on the report for your incorrect data, and if your code is wrong. You will get docked if your code is wrong, but if you know how to, your report, the goal is, in your report, do you know how to display your data? Do you know how to get data and communicate it? So it doesn't matter if it's correct data, it's just that it's there. Okay, let's go ahead and get started. So this week we have 2 sets of material. Today we are going to be talking about linear independence or linear independence or dependence, however you want to phrase it. And then on Wednesday we are going to talk about eigenvectors and eigenvalues. And they're both they're shorter sets of material, which is why we're covering 2 in 1 week. It also gives us time next week to do all exam review. Speaking of the exam, I now have all the details. So for the final exam, we are not using Lockdown Browser. You are going to have access to all your notes, everything. So open note, open book. You can also use MATLAB as a resource. There are going to be 6 questions on the exam focused on linear algebra. Like I said, we will do review next week. But your questions are not going to be as simple as type it into MATLAB. You're going to have to solve for something, and then you can check if your answer is correct in MATLAB. So like I said, we will do all of that review. I just want to let you know what you will have access to. Hopefully it eased some of your guys' stress levels when it comes to finals. But we agreed on that. So I call that a win. So make me proud. Yes, so this week and next week, or this week and Wednesday, today and Wednesday, 2 different sets of material. Like I said, today we are covering linear independence, which is a bit more theoretical concepts. And the goal behind week E types of systems equations material is to looking at a system of equations. We're starting to look at what types of systems we have. What information are we given? What kind of information are we given? What kind of information can we solve for? So MATLAB can be used but not needed for, MATLAB can be used but it's not needed. It's not needed. It's a resource. It's not needed. None of the questions say do this on MATLAB. It's just you can check your answers on MATLAB if you have time at the end, but it is not needed. Everything will be written on paper. Oh, and I want to note you'll have 2 hours to do the final exam for doing the exam and submitting. So make sure you've got your scanning process down. So you know you're going to scan, combine all your files, and submit, etc. Okay, so like I said, this week we are doing a little bit more theoretical stuff. We're really talking about types of systems. It'll be noon to 2. But yeah, it's in that time frame, 1:45 to 2:45 time frame. It'll be noon to 2 is your final. On Tuesday in like 2 weeks. Crazy. I don't want to think about it. Let's not think about that. We still have 1 week of material. Let's focus on this. Focus on finishing the project, and then we can go on to the final exam. Okay, we will get there. 1 week at a time, 1 day at a time. Right now, we're focusing on linear independence and independence. So like I said, when we're talking about this set of material, we're really talking about systems of equations in a more theoretical sense. What does it mean when we have a system of equations? So if you think about a system of equations, let's say we have 3x plus 7y plus 2z equals 45. Big number. If we have 3 unknowns, in this equation we have 3 unknowns. In general, the rule of thumb is you need the number of equations for every number of unknowns. So if I have 3 unknowns here, I need 3 equations in order to solve my system. So I need 2 more equations. So 4x plus 2y minus z equals 10, and negative x minus y minus z equals 1. So here are 3 equations that I can use to solve for my 3 unknowns. This section takes it one step farther. This section says it's not enough that you need 3 equations for 3 unknowns, or 4 equations to solve for 4 unknowns, or 5 equations to solve for 5 unknowns. We need 3 different independent equations. I need 4 different independent equations, 5 different independent equations. And it makes sense when you think about it like this. So let's say I have equation 4x plus 4y equals 4. This is an equation. I have one equation, 2 unknowns, x, y. And let's say I also have an equation that says x plus y equals 1. There's 2 equations. 2 equations, 2 unknowns. In theory, I should be able to solve the system. But in reality, I just have the same equation twice. If I divide this equation by 4, I end up with x plus y plus 1, which is equal to my other equation. So here, even though I have 2 equations and 2 unknowns, I really only have one piece of information. I have one equation twice. So when we're solving systems of equations, when we're putting together systems of equations, we need independent equations. We need what's called linearly independent equations. And that's what this chapter goes after. Okay, so we're going to talk about this chapter a lot in terms of vectors, but really think about each, when we say vector, we're really talking about equations. So I could write this equation as a vector. I could write it as 1, 1 for just the A side, or I could write it as 1, 1, 1 for the B side, for the A and B side. Okay, so when we're talking about equations, we're really talking about, or when we're talking about vectors, we're really talking about equations. Okay, one other thing to mention for this chapter is this idea of span. So there's a lot of videos for this chapter, for this week. I'm sorry, it's just the nature of the material. It's a little bit more theoretical, so it's harder to, so there's a lot more background information to cover. But one thing to mention is span. So like I said, we're a little bit more theoretical. We're starting to talk about spaces. So when we talk about spaces, I'll draw it up here. When we're talking about spaces, we're really talking about literally a 3-dimensional, 2-dimensional, 1-dimensional, 4-dimensional space. So if we have a vector with 2 numbers, this vector lives in a 2D space. It's 2-dimensional. It's in a 2D space. I can graph it. 2, 1, it looks like this. Same thing for a number in 3-dimensional space. This vector here lives in a 3D space. Another way to phrase this is with R2 or R3. These are the same. R2, this number here, R3, it's math notation for the set of real numbers. The set of real numbers, it's really just a 2-dimensional space. So these are the same. It's hard to go in the math notation when we're not in like a math heavy course. Like it's not my job in this class to like hone in on what this R means or what space means theoretically. We're just introducing these ideas. You'll probably see this notation later on in your math classes. Okay, but when we say R2, it means a 2D space. When we say R3, it means a 3D space. It's just the space that our vectors live in. So a 2-dimensional space, it's literally a plane. A 1-dimensional space, so 1D, would be R1. It's literally a line. 2-dimensional space is like the XY plane. A 3-dimensional space is all of 3D. It's the big cube that life exists in. 4-dimensional space, so R4 would be a vector with 4 numbers. Technically, that is a 4D space, whatever a 4D space looks like. But these are the same. So when we're talking about what's called span, we're really trying to talk about where our solution set can live. So given a system of equations, the span, where is it? Span, here we go. There's the word span. The span is the space that our solutions can live in, okay? We are very theoretical. I have this equation for span that you guys might find very useful. Once again, if a lot of this is just not making sense, that's fine. Like I said, it is very theoretical. I grasp it a little bit more every time I teach, but that's because I'm being reintroduced to the idea, to the material. But the span of a set of vectors is a blank D space in R blank. So we have these two blanks that we can use to identify the space of a set of vectors. And like I said, when we're talking about vectors, we're really talking about equations. We're talking about the span, we're talking about the set that our solution can be in, the space that our solution can be in. So the span, or the solution set of vectors, of a set of vectors, is a blank D space in R blank. So this first blank comes from the number of linearly independent vectors we have. And this second space comes from the space my vectors live in. So if they live in 3D, it's going to be R3. If they live in two-dimensional space, it's going to be R2. If they live in four-dimensional space, it's going to be R4, etc. So before we use this equation, though, we need to figure out what blank goes here. This one's easy to find because we just count the numbers in our vector. This one, though, we need to first figure out the number of linearly independent vectors we have, or the number of linearly independent equations we have. So let's look at an example. There are multiple ways to find out if a set of vectors is linearly independent or dependent. So let's say I have these three vectors. Remember, vectors, equations. I could rewrite this as negative 2x plus 3y minus 2z equals something. So it doesn't really matter at this point in time what our b value is. This one I can rewrite as 3x, nope, not 3x. 3y plus 3z equals something. And this one I can write as negative 2x minus 5y equals something. So really think about these three vectors as equations, as a set of equations. Okay? We're thinking about them as just the left-hand side of our equations. Our b values don't matter right now. So I want to figure out the span of this set of vectors. Yeah, it should be z. Thank you. So I want to figure out the span of the set of vectors, which means the span is going to be the blank D space in R blank. This R blank here is pretty easy. I just count however many numbers I have. 1, 2, 3, 1, 2, 3, 1, 2, 3. They all live in R3, and all of them should be R3. Or should be in the same space. So here's R3. I've got that done. This one, though, I need to figure out the number of linearly independent vectors. Okay, so independent, not dependent. Okay, there's a couple ways we can find out if some vectors are linearly independent. The first way is to write them as a linear combination. So a linear combination, as you already know, is going to be a scalar times a vector plus a scalar times a vector plus a scalar times a vector, etc. equals another vector. So I'm going to set it up so that C1 V1 plus C2 V2 equals V3. And now I'm going to solve for C1 and C2. So here we go. C1 V1 plus C2 V2 equals V3. And then I just solve it. So Flora, that's a good question. It's R3 because there are 3 elements in each vector. So this one exists in R3, this one exists in R3, and this one exists in R3. They're all in 3-dimensional space. And when you have questions like this, they will all have the same number of elements. They will all live in the same space. So it's based on the number of elements that are in each vector. Okay, so I'm figuring out how many, or if my vectors are linearly dependent or linearly independent. So the first way I can do that is I can set them up as a linear combination. So I have C1 V1 plus C2 V2 plus or equals V3. So if I do this, I end up with negative 2 C1 plus 0 equals negative 2. This immediately tells me that C1 equals 1. Sorry for my pen glitching. This second equation tells me that 3C1 plus 3C2 equals 0. And this one tells me that C2 equals negative 1. So I already have them. I can use my last one to check. -2 times 1 plus C2 times -1. Oops. -1 times 3 equals -5. And that's true. Okay, so there we go. I found that C1 is 1 and C2 is 1. That means that I can write my vectors like this. It turns out that V3 is just some combination of V1 and V2. Which means V3 is not new information. It means that V3 is just repeated information that I already know from V1 and V2. So this tells me that these vectors are linearly dependent. These three vectors are linearly dependent because V3 can be written as a linear combination of V1 and V2. And it turns out V2 could be written as a linear combination of V1 and V3, and V1 can be written as a linear combination of V2 and V3. So they are linearly dependent. If I had ended up with a situation where C1 equals 0 and C2 equals 0, if I had ended up with this situation, then they would be independent. So if you set up your vectors as a linear combination, you solve for your constants, and you end up with constants that aren't all 0, they are linearly dependent. If you end up with constants that are all 0, they are linearly independent. So for this instance, I ended up with C1 of 1, C2 of -1. That means my vectors are linearly dependent. So we can use a linear combination to figure out if a set of vectors is linearly independent or linearly dependent. So if I go back up to my span equation, this number here is going to be filled with the number of linearly independent vectors. That's a good question, Danny. What if you plug in C1 and C3 to this last one, and it doesn't equal the other side? Then either you solve them wrong here, or you have a bunch of conflicting information and you have no solution, which means you need to approach it from another method. That's a good question. I was actually running into that situation this morning, and it was driving me nuts. And I was banging my head proverbially against the wall, and I still didn't figure it out. So, yeah, that's a good question, though. So if you ever run into a situation where your system of equations doesn't make sense, that means that there's conflicting information there, and you're not going to have a solution. So you need to approach it from a different method, which we will talk about. Okay, so span. This number needs to be the number of linearly independent vectors. If I set up my vectors as a linear combination, you're not directly going to be given the number of linearly independent vectors. You're only going to be given whether or not your set of vectors is linearly dependent or independent. So the second way we can check for linear dependence or independence is using called the rank of a matrix. So in order to find the rank of a matrix, we are going to combine all of our vectors into a single matrix. And it doesn't matter if they're rows or columns. I'm going to make them rows. So I'm going to make it row 1. So here's V1, V2 is going to be this one, and then V3. I did columns this morning. Hopefully it doesn't bite me in the butt as rows. Okay, so you put them all into rows, and then you're going to reduce it into REF, to row echelon form. You're going to do Gauss elimination more or less. So first I'm going to say row 3 equals row 3 minus row 1. So row 1 doesn't change. Row 2 doesn't change. Now I'm making this a 0, so it's going to be -2, 0, -5, minus, or plus 2, negative 3, and 2. So I end up with 0, negative 3, and negative 3. Then I'm going to make this a 0. So row 3 is going to be row 3 plus row 2. Row 1 isn't changing. Row 2 isn't changing. And row 3 now becomes 0, 0, 0. So I've got my lower triangle of zeros. I've got it in row echelon form. The rank is equal to the number of non-zero rows you have. So this one's 0, not 0, not 0. So the rank here is going to be 2 because I have 2 rows that have non-zero numbers. So 2, this tells you the number of linearly independent vectors in your matrix. And it doesn't matter if they're rows or columns. So given these 3 vectors that I put into this matrix, 2 of them are linearly independent. That means I have 2 pieces of information, and the third one is just a repeated piece. It's the same as the other 2. It doesn't give me any new information. So to find the rank of a matrix, we can use rank to figure out how many vectors there are that are linearly independent. We put all of our vectors into a matrix. It doesn't matter if they're rows or columns. I put them in as rows. I reduce it to REF, to row echelon form. I get my lower triangle of zeros. And then whatever I end up with, I count the number of rows that are not 0. So this one has non-zero numbers, and this one has non-zero numbers. 2 total. That's how I got my 2. I count the number of non-zero rows there are in REF. So since I have 2 non-zero rows, that means I have 2 linearly independent vectors in my matrix, which means we can fill out our span. So there are 2 linearly independent vectors in this set. So that means their span is a 2D space in R3. That means that my solution set exists in a plane, so a plane in 3D space. So if that's 3D space, a plane in 3D space, however the plane is oriented. So if we look at this table of span, it's pretty useful over here. It gives us all of our different options for span. So if we have vectors that live in R2, so if they are composed of 2 numbers, so 2 and 3, that's a 2D vector, then I can either have one linearly independent vector, where they're literally just the same vector twice, so -2, -3. So this is literally the same vector twice. One's just the other one minus 1. So if I have one linearly independent vector, then the span is going to be a line. It's a 1D space in R2. It's a line. If I have 2 linearly independent vectors, so let's say I had -2 and 4, these are 2 different vectors. So if I have 2 linearly independent vectors, their span is going to be R2. So a 2D space in R2, all of R2, the entire XY plane. If I have 3 vectors, or if I have vectors in R3, I have 3 options. I either have vectors that are all the same. They're literally there's one vector, one piece of information, just duplicated. That span is going to be a 1D space in R3, so it's just a line. If I have 2 linearly independent vectors, then they're going to span a 2D space in R3, or just a plane. And if I have 3 linearly independent vectors, then they span all of R3. So they cover all of R3, which means their solution set is all of R3. It means it doesn't matter what B is, I can have a solution. So those are my options if it's an R3. For R4, I have 4 options. there's one linearly independent vector, that's going to be a 1D space in R4. If there's two linearly independent vectors, there's going to be a 2D space in R4. If there's three linearly independent vectors, it's a 3D space in R4. If there's four linearly independent vectors, it's a 4D space in R4. So those are all of my options for span. And I forgot to mention this morning, I'll email it out. There is this theorem that I forgot to put in the notes that states that if we have a set of vectors that are not zero, that exist, so the number of vectors is n, that exist in Rm. So here's the number of vectors. This is the number of elements. If the number of vectors is greater than the number of elements, then the set of vectors is automatically linearly dependent. So if I have 3 vectors in R2, it's automatically dependent. If I have 4 vectors in R5, if I have 10 vectors in R3, it's automatically dependent. So let's say I have 3, 2, 1, 3, 4, 5, 2, 1, 7, 4, 5, 6, 9, 8, 10. So here I have 1, 2, 3, 4, 5. N is 5, the number of vectors. And they exist in R3, or M is 3. Since N is greater than M, without any calculations, I automatically know that these vectors are linearly dependent. Okay, so that's just a theorem. Any 3 of them might be linearly independent, but altogether they're linearly dependent. I might have 2 linearly independent ones, I might have 3 linearly independent ones, I might have 1 linearly independent one, but altogether they are linearly dependent. Note to self, that was 33 minutes into the video. I need to email that out to section G, because I forgot to tell them this morning. Okay, so that's span. Fun span. It's very theoretical, so just think about this equation. How many linearly independent vectors are there? What space do they live in? How many elements are there in each vector? That will tell you the span. That will give you your solution space. Essentially, given a set of equations, where does your solution exist? Is it only going to be on a line? Is it only going to be in a 2D space? Is it only going to be in a 3D space? 4D space, etc. Okay, so given a set of vectors, we can figure out if they are linearly independent by setting them up as a linear combination, by finding the rank of a matrix. We can also, the third way we can find linearly independence is by finding the determinant of a matrix, of that matrix. So once again, if you want to use the determinant, then what you do is you put your vectors into a matrix. Once again, does not matter if it's rows or columns. I will do columns this time. So -2, 3, -2, 0, 3, 3, and 0 or -2, 0, 5. Keep in mind, this only works if you have a square matrix. You can't find a determinant of a non-square matrix. So this only works if you have a square matrix. Okay, so you can find a determinant using any valid method. It doesn't matter. I'm going to use our modified fish method for fun. Copy and paste my values over. And then I find my diagonals. So this diagonal, 2, 3, 5, is going to give me 30. This diagonal gives me 0, 0, -2, or 0. This diagonal gives me 2 times 3 times 3, or -18. Other side. Okay, -2, 0, and 3 gives me 0. 0, 5, -5 gives me 0. I really like zeros. They're great. And then 2, 3, negative 2 gives me 12. Okay, so the determinant of A is going to be, in my first set of diagonals, 30 plus 0 plus negative 18 minus the other set of diagonals, 0 plus 0 plus 12. Or the determinant of A gives me 30 minus 18, which is 12 minus 12. My determinant ends up being 0. Which makes sense, because using REF, I end up with my row of zeros. So since my determinant is 0, that means my vectors are linearly dependent. So this is another way that we can determine if a set of vectors is linearly dependent or independent. So we have 3 methods. We can set them up as a linear combination, solve for our constants. If our constants end up being 0, then they're linearly independent. If they end up being non-zero, they're linearly dependent. I can also use rank. Put all of my vectors, it doesn't matter their size, put all of my vectors into a matrix. Do row operations until you get to REF. However many non-zero rows you get tells you the number of linearly independent vectors there are in the matrix. So I forgot to mention, there are 2 linearly independent vectors. So all of the vectors, all 3 vectors are linearly dependent. My beautiful handwriting. So only 2 of them are linearly independent, which means all 3 of them are linearly dependent. And then the third way is by using the determinant, where if the determinant ends up being 0, then our vectors are linearly dependent. If the determinant of A ended up not being 0, then they would be independent. So we have 3 methods we can use to figure out if a set of vectors is linearly dependent or independent. Okay, like I said, we care about this. We care about this because our set of vectors tells us about our system of equations. Danny, yes. So rank is the only way to find the specific number of linearly independent vectors. So you can kind of deduce it based on your linear combination. It really just depends on how big your vectors are. If you have a smaller set of vectors, then you can kind of deduce it based on linear combination. But in general, the safe way, if you're looking for the exact number, is to use the rank. It's a good question. Now I'm going to go back to the notes, and I'm going to scroll all the way down to the bottom, because there's this table down here that I like to use to illustrate essentially why we care about this stuff. So given a system of equations, we have 3 options. We can either have one unique solution, we can have an infinite number of solutions, or we can have no solution. Those are our 3 options. And we can determine what kind of solution we're going to get by using these ideas, using the idea of linear independence and dependence. So here I have a bunch of different systems of equations. They're already in REF form. And we're going to fill out this table. So here I have a system. I've got my lower triangle of zeros. It's nicely in REF form. If I want to find the rank of A and the rank of AB, determinant of A, type of system, number of solutions. When I say rank of A, I'm talking about this part of our matrix. When I'm talking about AB, I'm talking about the entire augmented matrix. So for the rank of A for this system, I'm really only looking at this side. I'm looking at this matrix. Remember, the rank is the number of linearly independent row, or no. The rank is the number of non-zero rows I have after I've put it into REF. I already have it in REF. Oh, I'm not that tired. I don't know why I keep yawning. Probably because I've been talking for so long. But if I look at this matrix, I have, this has non-zeros, this has non-zeros, and this has non-zeros. So the rank of A is going to be 3. Because I have 3 rows that have non-zero numbers. If I look at the rank of AB, I'm looking at this entire matrix. It doesn't matter if your rank matrix is square or not square. It does not matter. It's still always going to be the number of rows. So this one is not 0, this one's not 0, this one's not 0. So the rank of AB is also 3. And it turns out if your rank of A is 3 or equal to the number of rows, your rank of AB is also going to be that same number. If I find the determinant of A, it's going to be really simple. It's a triangle matrix. The determinant of a triangle matrix is just the numbers along the diagonal multiplied by each other. So 2 times 3 times 1. The determinant of A is 6. Note that is not 0. And if I try to solve the system, I'll actually get a solution. I have one solution. So it's a unique solution. Anytime you have at least one solution, you're going to have what's called a consistent system. So this system is considered consistent because it has at least one solution. So if we look at this row here, if we look at this chart that we're filling out, the rank of A is 3, the number of equations is 3, so my number of equations is 3. The rank of AB is 3. My determinant is not equal to 0. And I end up with a consistent system with a unique solution. Okay, so let's look at my next one. So here is another system of equations. It's in REF. Here's my lower triangle of zeros. And if I look at the rank of A, if I look at this side over here, I have only 2 rows that are not 0. If I look at AB, if I look at the whole thing, I have not 0, not 0. That's all 0. My rank of AB is also 2. This 0 extends all the way across. So this means that I only have 2 linearly independent equations. I only have 2 pieces of information when I need 3 for a unique solution. However, if I try and solve this, I can get an infinite number of solutions. I'll just have my solution in terms of x3, in terms of a free parameter. If I look at my determinant, it's going to be 2 times 4 times 0. My determinant is equal to 0. And my system is still going to be considered consistent because I have at least one solution. I have an infinite number of solutions, so it's going to be consistent. So if I have a unique solution or an infinite number of solutions, my system is going to be consistent. Okay, so let's look at the next one. The next one isn't technically in REF, but all I need to do is just swap these 2 rows. So it's practically in REF. If I look at the rank of A, on this side I have not 0, not 0. My rank of A is 2. If I look at the rank of AB, not 0, not 0, not 0. The rank of AB is 3 in this instance. This 0 row does not extend here, does not all the way extend into my B vector. If I look at my determinant is going to end up being 0 as well, because I have my 0 row. And if I try to actually write the solution here, so if I actually try to write it, this first equation will tell me that x plus 2y minus z equals 2. That's fine. This one, however, tells me that 0 equals 4, and this one tells me that 7y minus 4z equals negative 2. This equation's fine, this equation's fine. This one, however, tells me that I have some conflicting information. 0 equals 4, that doesn't make sense. That's never going to be the case. So in this instance, we would have what's called conflicting information. where it's going to end up with x equals 4 and x equals 5. That's just not possible. You can't have x equal to two different numbers. You need x equal to the same number in every single equation. So when we end up with a scenario like this, we end up with 0 solutions. There is no solution. And it's an inconsistent system. So if we look at this chart, it gives us a lot of information. If the rank of A is 3, if the rank of A is the same as my number of equations, rank of AB is also going to be 3, which means my determinant isn't going to be equal to 0, which means my system is going to be consistent, which means I'm going to have a unique solution. So this column here, or this row here, all I need is one piece of information and I can figure out the rest. If you tell me that it's a unique solution, I can tell you it's going to be a consistent system. I can tell you the determinant isn't equal to 0. I can tell you the rank of AB is equal to the rank of A is equal to the number of equations. So all you need is one piece here, and it will immediately be able to tell you about the other pieces. For these ones, you need a little bit more information. So for this one, if you are told that you have an infinite number of solutions, you know it's going to be consistent, you know the determinant of A is going to be equal to 0, you know the rank of AB equals the rank of A, and it's less than the number of equations. If you're told there's no solution, you know it's an inconsistent system, you know the determinant of A is equal to 0, the rank of AB is not equal to the rank of A, the rank of AB is going to be greater than the rank of A, if you're told the determinant of A is equal to 0, then you have one of two options. You either have this row situation or this row situation. If you're told the rank of A is less than the number of equations, same thing. So depending on what piece of information you're told, you should be able to deduce at least your options. That's what this section here is talking about. And I created this nice little flowchart that kind of helps us identify working through a given set of equations. So we have two different scenarios. We have AX equals 0. So this is called a homogeneous system. And that's where our B vector is equal to 0. Or we have all zeros. We'll actually see this in play next week. So if we have a homogeneous system, it's always consistent. That means we at least have one solution. We're either going to have a unique solution or an infinite number of solutions. And whether or not we have a unique solution or an infinite number of solutions depends on the rank of A, or it depends on our determinant. So if our determinant is not equal to 0, we have the unique solution. If our determinant is equal to 0, we have an infinite number of solutions. Another way we can figure out is if we know the rank of A. If the rank of A is equal to the number of equations, then it's a unique solution. If it's less than the number of equations, then it's an infinite number of solutions. So we don't even need to know much. Well, I guess we need to know about the B vector in this instance, but really it's all dependent on A. A tells us how many solutions we're going to have. If we have a non-homogeneous system, or non-homogeneous, homogeneous is another way to say it, then we can have all three options, either a unique solution, an infinite number of solutions, or no solution. If our determinant is not equal to 0, we automatically have a unique solution. So as long as our determinant is not equal to 0, we are going to have a solution. We can solve our system for one solution and be done with it. We can use any method we want to solve our system. However, if the rank of A is less than the number of equations, so if the determinant of A is equal to 0, then we have two options. We either have an infinite number of solutions or no solution, which means we need to go to our rank. So if the rank of A is less than the number of equations, then we also need to look at the rank of AB. And so the rank of AB is equal to the rank of A, and the determinant is equal to 0, we're going to have infinite. If the rank of A is less than the rank of AB, then we have no solution. And so we can use these concepts in order to figure out what type of system we have, what types of solutions we're going to have. Do we have a consistent system with at least one solution, or an inconsistent system? Do we have a unique solution? Do we have an infinite number of solutions, or no solution? All of these concepts tell us more or less what type of system we can have. And like I said, it's very theoretical. And it lives in that arbitrary space that students tend to not prefer because it means you've got unknown variables. But the idea is that we need a set of independent equations, linearly independent equations, the same number of equations as we have unknowns in order to solve for our unknowns, and we need to check to make sure what type of situation we're going to end up in. Okay. That is all I have for today. So with that, we're going to end a little early, which isn't a bad thing. With that, are there any questions that anybody has to finish up? If not, I will see you guys on Wednesday. So final questions. For homework 12, P3D, when it said to verify part A, should our L be a lower triangle matrix? Yes. Your L should be the lower triangle matrix because that's what you'll compare it to in MATLAB. MATLAB will give you the strict lower triangle matrix form for L. It's a good question. Most of you guys probably didn't even think about homework 12. Should B be a logical array in MATLAB? Like your vector B? We shouldn't really be working with logical arrays right now. Danny, if you have a quick question, sure, I can answer a quick question about the project. So if I ran your T-fork parameters part A, if I ran your T-fork parameters function, it should give me one table based on the inputs I sent it. So in theory, for your report, you are going to run your part E code 10 times. That's one way to do it. You could individually run your code 10 times. You could also just write a script file that just calls your function with all those inputs by themselves. But I don't need code that displays all 10 tables. I need your part E code and all your other functions so that if I entered in those parameters for part E, it would print out the table corresponding to the parameters that I entered in. I think that answered your question. So Flora, yeah, so Flora, okay, that makes sense. That's one way you can do it. You can also just show that P times A gives you an answer and L times U gives you an answer, and it's the same matrix. Whatever you do to verify, that's fine. If you get a logical array, not a problem. Just make sure you give us all of your code that you use to verify. Yeah. Any other final questions? If not, I will see all of you guys on Wednesday for our last set of material. And we got this.